Hello friends, welcome to the channel. My name is Harshal. So today we are going to see moment of inertia and calculation of moment of inertia for continuous mass distribution. So moment of inertia, which is denoted by capital I. So first of all, what is moment of inertia? The quantity analogous to mass includes not only the mass but take care of distance wise distribution. The important line is take care of distance wise distribution of the mass around the axis of rotation. So moment of inertia is what? It is nothing but rotational analog of mass, which depends on 2 points. First one is what? First one is individual mass, individual masses. First one is individual masses, and the second one is distribution of these masses about given axis of rotation. Distance distribution. I am writing it in a short. I hope you understand what is moment of inertia. Moment of inertia is nothing but rotational analog of mass, which depends not only on individual masses but also take care of distance wise distribution of the mass around the axis of rotation. So this is an axis of rotation. Here it is the angular velocity. Here it is the different masses m1, m2, m3, m4, etc., etc., mn number of, and they have different number of distances r1, r2, r3, r4. We are going to conclude that here m1 mass have different distance, m2 mass have different distance, r2, m3, r3, m4, r4. So the moment of inertia concludes that it is the rotational analog of mass, but also take care the distance wise distribution of the mass here around the axis of rotation. It is what? Axis of rotation. It is a rough diagram of moment of inertia of a body of n particles. They have n particles. What are the masses? Masses are the mass of n particles. It is the mass of n particles, and here we are going to see the moment of inertia for continuous mass. So first of all, are you know that what is the continuous mass? For example, let's take this an a pencil. This is an glitter. This is an highlighter. What are they? They are continuous masses because they have number of n particles. That number of n particle pencil have different size. Also, they have different number of particles. They are what? All around us, which have number of sizes, number of shapes. They are called continuous mass. So, according to law, we conclude that, or according to the scientist, they told that I is equal to mr square. You know that I is equal to mr square, where I is moment of inertia. For example, let's take this is an axis of rotation. Here point A to B, and at C, here written at C, there is a mass m1. So, and it is the radius, or we can say distance between mass and the axis of rotation. So the moment of inertia is product of mass and the square of distance between axis of rotation and the mass. This is an inertial moment of inertia. So we are going to see this moment of inertia for continuous mass. So let's headline it. Moment of inertia, short form MI, for continuous mass. So let's take this is an axis of rotation again. This is an a point A, this is an a point B, this is an a point C, this is an a mass, this is a distance between mass and axis of rotation. This is axis of rotation, and we know that IAB, according to this IAB or IC is equal to mr square. This is continuous, so this is a simple form of moment of inertia. Now we are going to see this for a continuous mass distribution. So this is again axis of rotation. Now the particle, the mass is going to change. This is some example of any continuous mass. Suppose this is an example of any mass which have number of sizes. So this is a point A, point C, that point C, and here it is a mass. So continuous mass, they have different number of particles, so different number of mass, so different number of radius. So here we consider a dm. So what is dm? Dm is a differential quantity of a mass in a whole uniform body. Means they have different number of n particles, so n particles have different number of masses. So we are going to consider a small or an added quantity or a very small quantity of a mass, which is dm. So according to the law, the all moment of inertia, all summation of moment of inertia is all sum of individual particles. For example, we want to consider, or we want to calculate the total moment of inertia from the axis A to axis B. So we are going to conclude all the masses, means mn rn square. So it is the summation I is equal to 1 to n. So this is an equation where we are going to consider that if you want to calculate the whole inertia, whole moment of inertia of a continuous mass, so the formula is summation of all inertia, all individual moment of inertia. But it is not possible to calculate individually one by one. So that's why we are going to consider and a quantity on a calculus equation, which is going to be integration. So by use of integration, we are going to calculate the total moment of inertia of continuous mass. So we know that I is equal to mr square. We saw it. So first of all, differentiate both the quantities. So d means differentiating. So d is equal to dmr square. Here I am going to write differentiating. And now we are going to integrate. Differentiation and integration are opposite of it. Differentiation means the smallest, we are going to consider a small size or a small part of that particle in a whole body, and integration means all summation of small particles and concludes a whole body. So integration means we are going to sum up all the small quantities. So d is equal to dmr square. Here I write integrate. Here differentiate, here integrate. So we know that differentiation and integration are both so it cancel it out and we remain with I, and it is the formula, and I write r square first and then dm, and this is the nothing but what is this? This is the formula, final formula of moment of inertia for a continuous mass. Means if we consider any type of particle or any type of mass, and the axis of rotation is this, and if we want to calculate the whole moment of inertia of m1, of m2, of m3, so we are going to integrate the distances, whole distances of between the axis of rotation and the mass, and product it with the differential quantity of mass. So this is the important formula which we are going to use in numericals, in applications, which is equal to I is equal to integral of radius square into differential of mass. So I hope you got it. This is a simple derivation of moment of inertia of a continuous mass. If you understood the concept, please like the video and share with your friends. So bye bye.